I'm Dale, and then I'm a fifth-year graduate student in Department of Statistics, and my advisor is Dr. Group. And I'm studying. My research topic is about breaking Bayesian problem in this supervised version. This is my research topic. And for grading, I will be on this you submit your assignment. And what else?
I think this is how the grading scheme will work for a moment. So you're going to get 1 of 4 grades on each problem. It's going to be either a -1, this is per problem. And so I'm going to pull out some examples and show them, here's a -1, here's a -2, here's a -3, and we'll talk it over about. And also, stick breaking is a Bayesian sort of thing. Usually processes, cluster analyses, so you're doing advanced things. So did you take the advanced things class? Yeah. Okay, so he jumped right over this one and landed in the advanced things class. That's an important thing to mention. So he's more advanced than some of this. And we don't use stick breaking in here, but if you guys want to talk about it with me. A -1 means minor mistake. Minor error, it's like, what would a minor error be? Let's say you were graphing something and it was continuous and you decided to graph it as a bar chart. So he's going to mark it off -1 just as a heads up on statistical practice. Why not like connect it or tell us what this is? So if you've done something clumsy with algebra, it'd be easy to make that mistake. We see it all the time. We'll just clean it up for you and tell you -1. It really doesn't, we don't think that you don't understand the concept, and we think that the error is so easy to make that it's easy to not recognize. So minor mistake. -2 is also a minor mistake in the sense that it's easy to correct, but you should have recognized it. So minor mistake. You should have recognized it. So what I mean is, like, if you're computing variance and the variance is 5, but somehow right at the end you said -5. It's like variance has to be positive. So this would be a very easy thing to write down incorrectly because you've been double negativing, but you didn't recognize at the end, variance has to be a positive pointer. So something you should notice the answer doesn't make sense. And so that's a little bit subjective. But I assure you, neither one of those is going to move you a letter grade in this class. So you could take a few -1s on the homework and wind up with a 95. You basically have full. There's also a -3, and this is where things get a little bit tricky. So I'm going to put a star next to it for you to pay attention. This means you've got a critical error in the way you've done the problem. So critical. You're like taking a matrix and pulling it outside of a bunch of vector multiplications in a way that's illegal. Like you're factorizing out a matrix, or you're shuffling vectors in such a way that they're not conformable and they can't multiply into each other. And if you do that kind of stuff on the midterm or the final, this sort of -3 thing that won't hurt you in your overall grade. I mean, they're really close to each other. So the homework's there to help you, make you practice and prepare you for the midterm or the final. If you make these kind of mistakes on a midterm problem, it's going to be detrimental. So, meaning it'll be big impact. Keep in mind that you give people midterm makeups. I'll tell you about that a little bit more. There'll be bonus points on offer, and I give extra credit. So I think even if you do make a couple serious mistakes on a midterm, there's another pathway to build your grade up to an extra credit assignment. I'll have a couple of those listed for you. So be careful on this. The idea is that if you're practicing and it's a real honest attempt, I don't want to ding you for that. So I want you to be able to practice and learn from the mistake. I know for me, some of the mistakes I've made, that's the stuff I learn the best. So I want you to have the right spirit as you're practicing. Now, if you don't do a problem, you get a -10. So you didn't do a problem. if you do 2 of these, so what I really mean is if you didn't do the 2 problems, so you get this twice, we're going to give you a 0 on the whole homework. So 0 on the homework. And here's my thinking on this. If you don't want to practice, we don't want to assess. So if you don't want to do the practice and learn from it, we're not going to grade it because we don't know what we're grading. We'll just give it back to you. Now, if you do push your luck on this, I'll probably say something like, go turn this in. Go do it by the end of the day, or can you do this problem, or something like that. And I'll give you a little bit of grace if it seems reasonable. If it's an honest mistake, and you're like, oh, I had 3 pages printed out, but I lost the last one and I didn't see the problem, and it really seems honest, I'm going to leave it. And I'm going to say, go do the problems. So again, the homework's there to help you. So, and I'll give you points back if you made a mistake on grading. David, welcome. Seat over there. So that's the grading procedure. And if you have a problem with any of this, Jay Young's your man. Does that sound good? Yeah. So this is my strategy at all classes. So this is business as usual. So it kind of matters. Like and what Jay Young will do in the grade book is he'll indicate those. So in a separate column. So it might be that this never happens because I don't give you 10 problems on homework. I'll give you 6 multi-part problems or something like that. But let's just say hypothetically, you incurred that 10 times, or let's say you incurred that 3 times, or let's say, I can't do over there. Let's say you did this 9 times and you did that 3 times. Let's say that one more time. Let's say person A does this 9 times, and person B does this 3 times. Jay Young's going to indicate in his grade book how many of these things are in there. So that at the end, when you're having trouble in the class, I can look it up and go, oh wow, that's correlated with your practicing. So I think there's no secrets to life. The more you practice, the better you get. And that's what you want to do. You want to practice the problems. You want to ask questions about them. A good study strategy is to take all the problems I give you and change the distribution. So anything I ask you about a normal distribution, I bet you could do with an exponential. So I bet you could do in spirit the same sort of analysis on a mean or a variance or something like that. And so you can change the distributions. And that's what I'm going to do come midterm time. I'm going to look at your homework and I'm going to basically change the distributions. So same sort of calculations, but the algebra is completely different. So you can do that too. Jacob, you want to throw out a piece of advice? Advice? Still here? Did you guys get that? Let's all say it together. Start early. Is that what you said? Start early.
Start early, then attend all the classes.
As much as you can. So start early, ask questions, you will learn this material. You don't want to be halfway through this class and go, I wish I learned this stuff better. I should have started early. So don't do that. Let's just get started. Think about distributions. If we talk about a distribution in class, read the wiki page. Work a few problems from an old inference or probability book. Just to get acquainted. Like, let me make sure I can work out the expectation. So that's all assumed. I assume you know what an expectation is. You know how to take one. So I understand that some integrals are harder to do than others. But in spirit, you should know. So if you don't, start early and pull out your old probability book and start looking at it. Jacob, thank you very much. Should we put you down for an hour period on Zoom? Jacob. Zoom or in person, I'll let you decide what you want to do. He has some office space. Also, he'll meet with you. But let's just put down an hour and then we can set up a Slack page later. So I'll do that next week so that we can communicate with each other. And if JM has a particular place he wants to meet you, he can update you on the Slack page. And I'll post all of your VT email accounts to the Slack page so that we can get popular with it. I don't do that in the first week of class because there's too many shifts in the class. And so too many people need to be added to the Slack page later, too many people need to be pulled off the Slack page, so we'll do that in about a week. Jayum's going to be the person that looks at the Slack page at least every 2 days. And I'll check it every 4 days or something like that. Something like that. So I always hope Jayum answered the question right away. He's going to do stuff like that. Every once in a while, he'll do one of the review sessions. We're going to schedule that on Friday. And he's basically here to help. Okay, good. Thanks, Jayum. That's it, unless you want to sit there the whole time. Oh, sorry, we didn't read out.
What about everybody wants morning or afternoon? Any ideas? 10 a.m. or
Anybody have any problems with any 10 a.m. slots?
okay.
Alex? Monday, Wednesday, Friday are good for you?
No, we have a class.
Tuesday, Thursday? Let's just get some stuff down. Any strong opposition to Jayum's office hour being 10 a.m. Tuesdays? Going once?
How long are they?
An hour. Strong opposition? No, I'm going to also set up a review session. And then I always try to make sure I'm available for a half hour after class. So after class, I'll be sticking around. There might be once or twice where I can. And then I do the evening review sessions. So there should be a lot of touch points in here. So it's really set up that if you can't make something, you can make something else. Any other times you want to throw out a competitor? I hate just rejecting hypotheses without telling me something else. Like doing a debates, you have to set up my whole universe of alternative hypotheses.
So I have more opportunities like 11 a.m. Tuesday, and then 4 p.m. Monday, Tuesday, Thursday.
Hold on. You're never going to settle anything if you do this. Dylan, you opposed. Do you have an alternative?
Before this class and Tuesday.
Before this class? 11 a.m. Tuesdays.
Yes, we have.
You want Monday, Wednesday,
Is that when we have?
Yeah.
That's me and Frank's.
Frank's is Tuesday, Thursday. So
Okay,
before
that's-
You gotta give me an alternative.
I don't believe so. I know that. I'm on Tuesday, Thursday. Stats.
1 o'clock. Tuesday or Thursday?
Yeah.
Just go with 10 a.m. Tuesday.
Pretty short.
Yeah. If I need to, I can.
You can find Jada, so you guys work on the same floor, so I think everybody in the lines. Is that okay, Colby? So they can ask you questions when they see you around, right? Okay. This is the hardest part of this whole class, is just agreeing on a time to meet. So I'm gonna say 10 a.m. Tuesday. Okay, so the week opposition is satisfied with our other arrangement. Good. Okay, that's locked in. What else while we still have Jada?
And my office is more like, my official office is 4 Hudson, and then 4 Ali and 4 So you can see me 4 or 4
I'm gonna put this on the web page. So there's a syllabus that we have, so I can put in 10 a.m. There's a spot for that. There's Jayum's email address. So this will all get updated. So if you're not taking notes, this is going to be preserved in the video and also on the web page.
But I was just going to comment, if you can keep Zoom available, that'd be awesome, because my office is a long way away, so.
Okay, so Zoom. So Jay Young will set up a Zoom thing, not this week, because we don't need office hours this week. We'll get that all taken care of. Slack at the end of next week. We'll post the Zoom link there, and we'll get all the resources there as well. Good? Okay, good. Amazing. So sometimes that's a lot rougher. Thank you, Jay Young. I think in terms of hypothesis testing and the metaphor we were using, if you make your universe too big and unreasonable with too many choices, it can really mess up your selection of things and placing probabilities on things. We'll talk about that later. Thanks, Jacob. Cool. I'm still thinking Thursday for evening review sessions, maybe 6 p.m. So I'm going to tentatively say that. Any strong opposition to that?
Is that line up with no assumptions at all?
It obviously doesn't. So since I'm the host.
Yeah.
So it's giving me enough time to walk back. So 1 hour of reception, and after reception, we can walk back together. So I'm going to close out the tab. We'll walk back. That's why it has to be in class.
I only do class. Review sessions.
And the nice thing is I'm already here at that time. I kind of like it because it aligns with my schedule. Okay, I'm going to say evening review sessions unless there's strong opposition. We're going to be 6 p.m. Thursdays, and I'll announce these. So no review session this week. We don't need it. That's the hardest stuff, so I can complete the syllabus. Let's have a look at this. So this is where we were about leading off last time. This is my webpage. So leanin.stat.et.edu. You can click on courses taught. This is Bayesian Statistics. Click on that. And there's just some mumbo jumbo about all the topics we're going to cover. So you can read through that. We'll do all the things you expect me to do. MCMC, reference analysis, Jeffries, that sort of stuff. So we're going to build it up pretty gently. And so we're going to be using probably a binomial distribution and a normal distribution for the first couple weeks of class, just because we're kind of familiar with them. And then we're going to be building up from there, learning all kinds of new distributions. Distributions over matrices, things like that. So Bayesian can put a probability measure on anything that they want. We'll be talking about that. In the very beginning, we'll be starting with things like means of distributions. We'll be trying to learn what that mean parameter is, something like that. The syllabus is here. So I have a couple sections in here that I haven't filled out. So I need to come up with a midterm date. We're going to all check our calendars and come up with strong opposition for midterm dates around Halloween. So we still need to figure that out. I don't want to schedule too many things in one day. So check your calendars. That's still forthcoming. The final exam date is locked in for us. That will be in class. If you don't know, Virginia Tech reserves the time. So 7:45 a.m. on Friday. I apologize, but it could be worse. So it could have been Saturday. So Friday the 3rd. We've got the Zoom review sessions. That's going to be Jay Young in here. We've got the instructor review sessions. That's me. That's Thursday 6 p.m. So I don't need to change that. Bi-weekly as needed. I'll make announcements. So I'll put in something about his email address so you have all those resources. That'll be up by the end of the day or tomorrow. Okay, so we talked briefly about Peter Hoff's book. I'll bring in a copy of that and pass it around if you guys want to look at it. But I am a strong believer that you should have books that you reference in class. So regularly. You don't know an explanation for something, it's good to have multiple books so that you can read multiple explanations. And sometimes there's two ways to explain something and they're both right. So and that can be pretty cool. In Bayes land, that's very true. So there's sometimes you can have a whole bunch of objective properties simultaneously. Sometimes you can't. So it depends on what the author wants to explain first. So I've noticed that all Bayes books are kind of written a little bit different. So they all usually start out with the normal distribution, and we're going to even change that in this class. I want to start with binomial distribution, and I'll tell you why. For computing, you can use anything you want. I don't care if you build it up from ones and zeros. So, but I would recommend you use a language like MATLAB or R. They have some graphing facilities. So in this class, I'm going to present you with several simulation studies, and I love that because you'll be able to work out the math, know what the correct answer is supposed to be, simulate everything, and make sure it all aligns. So you can almost grade your own stuff out. That's what I used to do in college. I know how to do, maybe I would think I knew how to do the integral, I'd work it out, and then I'd do a Monte Carlo experiment to make sure I was close. Please.
Is BT providing the textbook? So if it is available as a PDF online, you can look for it.
That's true.
It's just saying, I found it on Google.
Access is provided through libraries.
It is, okay. You can also find it on Google.
Right, exactly.
Cool. Yeah.
Academic honesty, you guys are allowed to work together on things, but I want you to produce your own work in class. So if you look at somebody's work and they've got an explanation, and you use the same thing, just make sure when you're writing down your solution, you're not staring at their solution. So if we bring in carbon copies and stuff like that, JM is going to notice it, and he's going to want to do something else. JM is very, very strict, so let's not put that pressure on JM. So, of course, I'll give you a warning for that kind of stuff. Once we get to actual projects and stuff like that, I don't actually want to see your source code, but I want to make sure your graphics are original. You made them yourself. So, of course, they'll look similar to other people's, and your explanations. I don't think there's a lot of opportunity to take the steps in this class, so it's not much more. I have had to talk to people every once in a while where I think they're probably not doing their own work, and it catches up to you come midterm time. So that's what I really want to say from. Let's just make sure we're all here for the right reasons. If it's hard, good, that means we're learning. So if you need some extra help, that's what all the review sessions are for. Cool. Scheduling. So that's just worth looking at one more time. So we're going to kick everything off with this link right here. If you click on this, this is a PowerPoint presentation and introduction to Bayesian Statistics. Later on, we're going to read this paper, When Did Bayes Become Bayes? So does anybody know what this question is all about? When did Bayesian inference become Bayesian? What they're really asking is, when did we name it Bayes? What we're doing is Bayes. And so this paper is all about that. And I ask a couple questions related to this paper. There's a homework assignment here. I ask a few questions about it. So let's just look at homework 0. This isn't the due date yet. I haven't updated everything. I'm going to shift these dates around. I haven't assigned anything to you yet. So by next week, this will be updated with more relevant updates. But if you want to have a look at these, this will give you an idea of when things are going to be due. Keep in mind, we're starting the semester much later in the calendar year, this semester than last semester. So we started this semester on the 23rd, and last semester I think we started on like the 16th. So bear in mind there's a shift in here by about homework 0. You can look at it. You will be getting this homework 0. I'm very tempted to ask one extra question right here and put in a problem for you. This gives you some likelihood values. It gives you some probability values. These ones will add up to 1 right here. You want to check. So this is a discrete thing. Theta takes on various values. And I just want you to plot this stuff. And then I want you to compute using these numbers the expectation of theta units. So it's a stat 101 type calculation, but it lets me know that you're familiar with notation, and if I write something rather tersely, it lets me know you're in the right place. So, of course, if you need me to explain any of this, I'm happy to do it. It's meant to be an easy exercise. I also asked you to read this paper. When did Bayesian inference become Bayesian? And then I asked you two questions to this. So, who originally coined the term Bayesian, the actual word? And I tend to think that there's three reasonably correct answers to that question. So there's not just one. Of course, one person didn't come up with everything and copy everything. But we're going to just check to see if you're right. So come up with an opinion about this and we can discuss it. And then I asked a little bit more of a contentious question. Who's the founder of Bayesian Statistics? Does anybody have an answer to that? Who's the founder? Michael? Is that what you were going to say? Dylan said Bayes. Anybody else?
Jeffries?
Jeffries. So maybe. So we could probably have feisty arguments about all of this stuff. Jeffries comes much, much later than Bayes. So when was Bayes around? Jeffries? Much later, around 1900s. So they're like 100 years apart from each other. So I would say that those are not unreasonable answers. But read the paper and see if there's a little bit more. Steve Feinberg went through a great deal of effort to write this paper and try to answer this question as thoroughly as possible, and he wrote 30 pages about it. So just like most papers, I think the answer is somewhere in here in a small section. So if you want to skim the paper, that's good enough for me. I don't ask you to thoroughly read it. This isn't a philosophy class. I'm not going to ask you to write long essays on things, but I'd like you to touch on this question of when did this stuff happen? And what you're going to find out is this has been going on for 150 years. So, and it's being developed, and there's modern adaptations about things. So the field is constantly changing. And this paper does a good job of explaining some of that early development. Who was Jeffries? What was his field? Is he a statistician? He's not. He's a physicist. So he has specific problems in mind, and he needs particular analyses. So statistician wasn't a term until maybe the 60s. So 70s, and what it means today is entirely different from being an accountant. So we don't do actuarial science that often these days. Anyway, read the paper. I think it's kind of fun. The PowerPoint presentation. Let's look at that. Page intro. This is important. Want that first? Let's do that. Dylan wants the YouTube page. I get a little bit sometimes bored with doing too much theory at a time, so I'll switch over to computation. If I'm talking too much about administrative stuff, sometimes I like to jump gears and talk about something else for a while. So, but Dylan wants to keep us on track and look at the YouTube page. So those are here. So if you Google search Alina Lectures, it will bring you here on the first link. So I don't think that there's anything that coincides with this. These are all of my classes for maybe the last 5 or so years that I've recorded. Every once in a while there's a technical mishap and I don't have the video. And that's guaranteed to happen at least once or twice in this class. So my batteries will run out, I'll forget to format my SD card or something like that, and I'll get the end of it. So stuff happens. And sometimes there's just cosmic radiation. The camera doesn't work. So if you'd like, you can get started by going all the way back to Bayesian Statistics. This is going to be way back here, and I dated everything so that you can look it up pretty easily. So the beginning of Bayes is here. So this is 1 year ago. You can click on that. And we get an app. So you're going to get some lectures. And usually in class, I will write at the top of the board what the class is going to be about. So if you ever just want to skim it real quickly to see what lecture is going to be about and any announcements, you can just check in on that in 5 seconds. So I do hold you responsible for whatever I put up here. So that's where some announcements will be. If you don't like that, you can also read about it. So sometimes I put a few notes and I tell you what's coming up next time. So this says next time we'll begin our first Bayesian example. So we're finally past the syllabus. So this is like tomorrow's lecture or Friday's lecture. So that should be persistent for you. Use those responsibly. I don't want you to substitute being in this room with everybody for the videos, but there'll be times where you I like it when you guys email me and tell me you're out of town so I don't worry about you. So if you tell me you're going somewhere or you're going to miss a few days, let me know so that I don't have to do a welfare check. So I used to do that all through COVID, make sure everybody's okay, and I really want to your apartment. I don't mind, so send me a note. Let me know if you're okay. Dylan, anything else? Cool. We've got 18 minutes. Let's do a little bit of Bayes.
You're gonna throw a party for 1,000 subscribers?
1,000 subscriber special.
Is that how many I have?
You're at like 985 when I was thinking,
Wow. No. People have told me that I can blow up my page and get a lot of responses if I made it a little shinier. It's not the rule. It's light shine. This is a very brief introduction to Bayesian Statistics. You can call me whatever, all of these are valid. So don't mind, as long as you're not trying to offend me. So if you do accidentally do it, I'll let you know. I'd like to cover a little bit of stuff in Bayes, and I'd like to cover Monte Carlo as well. So I don't think you can really talk about Bayes these days without talking about Monte Carlo or variational inference or some sort of computational device to compute all this high-dimensional stuff. So I like to think about these things together. I'll give you a little bit of history on just Bayes in general, likelihood function. That's kind of the cornerstone of Bayes, so that's some stuff that you're taking home. But basically, a Bayesian analysis has 2 ingredients. It's the likelihood in the prior, and they result in the posterior. We're going to talk about those words, where they're derived from, and I'll probably tell you, I wish they named it something different. And so they probably would have circumvented a lot of argument. And then I'm going to tell you a little bit about Monte Carlo. We're going to start building in some simulation, and I'll have a simulation study. I did once upon a time, and I apologize to those of you that I've already shown this presentation to. We're going to veer pretty hard from your old class. So same starting point, the ending point's going to be good. So if you've seen this in inference, I apologize. But you at least know the answers to this. So once upon a time, I did a Google search on the word Bayes or Bayesian or anything with that root word Bayes in there. And Google goes through and it finds articles that are dated with significant dates that coincide with the word Bayes or Bayesian. And it plots the frequency of usage of that word through time. And so we see, interestingly, a little blip over here where Bayes is often cited, and it coincides with years right around 1760. Does anybody know the exact year that this is surrounded? What year they're usually referencing?
I'm not sure, but I hope it was
61. So we're close. Yeah, exactly. We could make 9 or 10 guesses. We'll see in a second. Bayes starts launching. So this is what Bayes looks like. Don't mind this, Colby. This is just some smoothing for however they plot histograms. And if you've ever made histograms, there's all kinds of issues with it. how you smooth it. I don't think it's actually going down right there. I think it's just pushing against this boundary. So even in inference, when we do estimation against boundaries, it's a little bit harder than apparently drawing history on expected boundaries. So anyway, I think this is an artifact of how they do searching. Also, the web scraper that's going around and crawling through everything and looking through everything, it also has less information later on. So, because it's not all stored in the same place. So there's always a lag on them. So if you're ever looking at like your Google Scholar pages, you'll notice, hey, why am I getting all these citations from 3 years ago? It's because there's a lag. So you have to update it yourself if you want. So Bayes is becoming tremendously more relevant as the years go on. See who was paying attention 6 months ago when I last gave this slide. What happens right there? Who's that?
It's not gossip.
That's Gaussian. So that's student T's distribution, he was Bayesian. So a lot of people think that, well, Bayes is something new and modern, and it kind of is, but Gaussian was thinking about Bayes long before a lot of people were. And he was talking about Bayes and he was interested. What's all this stuff over here? So all of a sudden there's something going on and shaking up the world, and it becomes ever more popular.
Fisher doing
Yeah, a little bit. There is Fisher, but it's just little chirps right around it. And I think Fisher arguing a lot starts happening more and more. So yes, he does mention something about Bayes, but I think it happens once in like 1935.
I don't know about the statistics side, but a lot of space-related problems would be done with control and things which would use space.
I see. So we're still thinking probably over on this end right here. So NASA, Apollo missions. That's much later. Metropolis and Hastings. What are they doing? Where were they hanging? Los Alamos. Yeah, we all saw Oppenheimer recently. That's kind of disappointing. So not enough Metropolis and Richard Feynman in there for my taste. Too much politics. That's computers. So I do think Metropolis is hanging out over in Los Alamos and they're trying to figure out the right electron configurations to blow stuff up. On the other side of the pond, there's Bletchley Park. So in there, cracking code. So the Americans were making weapons and the Brits were cracking code and doing intelligence work. A little bit different how they allocated their resources. I think there's a lot of Bayes chatter coming out of Bletchley Park. So I.J. Good, Alan Turing. So you can read about it. It's all in the paper. So it tells about this whole ramp up. There is some Bayesian thinking going on in America, but it's not much. And Metropolis, what he's doing with MCMC, he hasn't really thought about all of MCMC. He's doing it for a specific type of model. He doesn't have the full generalization of it, and he's not thinking about Bayes yet. So MCMC is a general purpose sampling algorithm. Bayesians utilize it later on. And I don't think Metropolis quite saw that readily instantaneously, or at least he didn't devise it that way. Okay, here's my evolutionary tree. Somebody said that they're into phylogenetics and coalescence type stuff. Is that you? Right on. So here's my lame attempt of coming up with the evolutionary history of Bayes. Anybody want to just point out what's obvious about this tree? Glosses at the top. So that's one of my answers for who one of the founders is. So, and you'll read about this. Where does Laplace come in? What does he start to say? So I say Laplace understands the implications behind what Bayes did. So Bayes came up with a probability rule, but he didn't argue an inferential rule. And that's what Bayesians are doing with Bayes' theorem. So statistics starts getting born. You've got Fisher driving out that all scientific questions can be measured and answered through data, through probability functions. So he's new to the table. Carl Pearson and him are fighting with each other. And so if you ever read history of statistics, you know what these arguments are about, and we're going to touch on them in this class. It's hypothesis testing. Even just the idea of what a sampling distribution even means, they have to argue about. I don't care how you think about a sampling distribution or what that histogram means, as long as you use it. So whether or not you think that reality is changing and these are degrees of reality, or these are just errors in measuring the same thing over and over again. So they argued very deeply on this, kind of a waste of time. Nathan and Pearson spin off of all of this, and they start to refine classical hypothesis testing. It's the counterpart to how Bayesians test, and we're going to talk about what Nathan and Pearson concocted. And if you've taken a full-blown inference class, you already know what they said. So they're measuring error rates and controlling error rates. And Bayesians are measuring beliefs. So that's the other side of the tree. So I can't talk about Bayes without talking about non-Bayes. So modern Bayesian methods start being developed. Bless you. Jim Berger starts thinking about Bayes from a decision theory standpoint. Alvin Gelfand helps devise the Gibbs sampler. And so there's both theoretical and computational reasons that are being developed in tandem for being Bayesians. Bless you. And it starts a whole slew of arguments in statistics. And they used to just kind of fuss and fight, I would say, up here on this part of the tree. But after the computationalists came in and showed everybody what you could do with Bayes, even the classical people and the frequentists sometimes start saying, well, sometimes I use Bayesians. I want to make sure it's frequentist. And so, and I kind of like that things start aligning and at least people are having the right conversation and distinguishing the right objectives of their analysis. Bayes' theorem is this. So this is an uncontroversial probability rule. We wrote this down last time. The way I wrote down the probability of B would have been different. I would have just written this down as the probability of B in the denominator, but I'm marginalizing out over A and the complement of A. So I've broken A up into two sets. Now, if A were continuously measurable, I'd have an integral at the bottom. But usually you have some sort of marginal probability down at the bottom. So that's Bayes' theorem, and we'll talk about this rule a little bit more, so I'm not done with the basic part of talking about it, but I want to take it for granted at least for a moment. So we'll go back to hamburgers and milkshakes or broccoli and cheese and explain it a different way a little bit later. But let's just take it as this theorem, and I'm going to say it's intuitive. And then if you don't think it's intuitive, you can let me know how I do next week when I try to make it for it. This probability rule, all statisticians use. All probabilists use. It doesn't matter if you're frequentist, Bayesian, classical, a fiducialist, or whatever your camp might be. Unfortunately, Bayes didn't get a chance to take glory for all of this. So Bayes didn't publish his paper before death. That is Bayes' grave. Instead, somebody finds the paper in 1763. So is where this starts happening. So 1763 is when Richard Price finds Bayes' paper. So he says, read December 23rd, 1763, I now send you an essay which I found amongst the papers of our deceased friend, Mr. Bayes, which in my opinion has great merit and well deserves to be preserved. Experimental philosophy, you will find, is nearly interested in the subject of it. Do you believe that's a compliment? So we write a little bit differently. And on this account, there seems to be a particular reason for thinking that a communication of it to the Royal Society cannot be improper. And then he gives the most pleasant salutation I've ever read in my entire life. That your inquiries may be rewarded with many further successes, and that you may enjoy every valuable blessing is the sincere wish of, sir, your humble servant, Richard Price. Way to kiss up. That's pretty good. So this paper got published. So, and we have this paper on our staff archive. So if you're fishing through our paper archive on our webpage, it has this paper in there, but nowhere where you would find this notation in there. So it's much, much different. The way they wrote about math is almost uninterpretable to me. So you have to be a historian to read this and mine this formula out of it. But he says it in a lot of words. There's a couple different ways you can write Bayes' theorem. So I'm going to write it down slightly different a couple different times, and I want to take us through this notation. But basically, here's a discrete way of writing down Bayes' theorem. If I had two different sets and I'm writing it discretely, where I've got set A and I've got set B, and I can take the same equation and write it a little bit differently and call this a likelihood function, where this function is going to be a function of this parameter theta. Now, those of you, Alex, are going, this is not how you usually write likelihoods. You're right. So I like to start out with a different way of writing it, sometimes the way that other people write it, but you can see that there's a little bit of pattern matching between the notations. So I'll talk about the discrepancies in writing down likelihood functions. As long as we're talking about the right thing, thinking about it in the right way, I don't care which notation you use. So it is true, Alex, that I usually do use a different notation. But I want it to match this. So this is just an adding of a function where I'm breaking up theta continuously and adding over it continuously. And I've got the same sort of patterns in here. Now I've really minced my notation around. So I've written down this is a posterior probability, and I've written this down with an R for probability, and it can't be an R. So does anybody know why? Because theta is continuous. And so I'm really talking about a density function, but I made this graphic a long time ago, so I can't edit it. But this R should be gone. This is a continuous function. So there's a little bit of abusive notation here, and I want to get us through this so that we have good reasons to be consistent about the notation. So theta is a continuous function, so I probably shouldn't be calling this a probability. This is a prior distribution right here, and this is a likelihood function. And that's where I want to really spend some time next time, dissecting what these things are. But what I want to do with this is I want to give you an example. So of a binary point pool, i.e. a model that can be modeled by the Bernoulli distribution. So where I can indicate a 1 or a 0 or a heads or a tail with probabilities associated with each other. So that add up to the whole possibility of space. So there's two possibilities, either see heads or tails, coin can never land on its side, and there's associated probabilities with those that don't. So binomial distribution. We're going to look at this distribution and we're going to concoct a Bayesian analysis on the probability distribution of P. So what we're going to be doing is we're going to be placing a probability distribution on a probability. So anything that I want to measure and have uncertainty about, I can do through a Bayesian analysis. So even if I'm trying to measure a degree of belief, I might have a degree of belief in that thing itself. And I want to talk about some of these confusing things, and I think I can do it all in the Bernoulli distribution, or a binomial distribution. Those of you that have taken an inference class knows it doesn't matter which one we use. We're talking about the same exact process. So next time we're going to start with our first Bayesian analysis. Walk through it very slowly, and then we're going to start speeding up and building in more distributions. So I think what I'll do is I'll teach you about Bayesian inference, how you come up with probability distributions on unknown parameters. Then I'm going to walk you through forecasting. And then I'm going to back up and I'm going to do it all over again with another set of distributions. So I'm going to first do it with the binomial distribution. I might slot in a normal distribution so we can just try again. Then I think we'll jump gears, we'll do inference, and then we'll pedal backwards, and we'll jump back to doing it all with different distributions. And then we'll scale it up. And then I'm going to teach you about computation. Then I'm going to teach you about hypothesis testing. So then I'll get tired of doing that, and I'll teach you more about MCs. So we're going to iterate concepts so that hopefully by the end it's super solved. So I think that this is an example forward class. So pay attention to the examples and build up your own examples. That's it for now, you guys. So we'll write down binomial distribution. If you want to get ahead, start early, remind yourself what a binomial distribution is. Remind yourself what permutations are and combinations are. So that'll make your life a little bit easier. Thank you guys.